for our first Saturday morning Astro of 2022. Welcome. It's nice to see you all here. We have a good number of people who have registered. I want to extend, we have people from California to New York to Texas, Canada, and outside the US. We've got about 15 students registered from 3 or 4 different schools in Colombia. So special welcome to all of you. It's nice to see you here. My name is David. I am the outreach coordinator for physics and astronomy here at Purdue. Saturday morning Astro is probably my favorite program. It always generates a lot of interest, and we have some interesting topics coming up for this year. Some things that we haven't done before. So you joined at a good time. Thanks for being here. We're going to do this morning a model of the solar system. When you look at pictures of solar systems, you never really appreciate the scale, the true scale of what you're looking at. If you look at the planets and they're big enough to see on a picture, for example, you have no idea of the distance between them. And if you look at the distance between the planets at that same scale, they'd be too small to see, less than a pixel. So it's hard to visualize the true scale of the solar system. And that's the whole purpose of this lesson. But we're going to start this morning with a presentation by Brodie Connor. So Brodie is a Purdue graduate. Brodie was a physics major at Purdue. He then went on to study planetary science, and he graduated last year and is now starting a new adventure in geology. Is that right, Brodie?
Yeah, that's right. That's correct. So I'm down at the University of Mississippi in geology.
Okay, so Brodie is starting a new degree, a new program, and life in a new science, but a related science. So Brodie, thank you for being here. I'm going to turn this over to Brodie to give a PowerPoint presentation of some aspects of planets and planet morphology, the evolution of planets, how our solar system came to be here. And Brodie, that's all I'll say. I'll turn it over to you.
Great, thanks, Dave. Let me go ahead and share my screen. Great, thanks, Dave. Yeah, so like Dave said, I'm Brodie Connor. I was at Purdue for about 5 years in physics and planetary science, and now I'm starting my graduate degree in geology at the University of Mississippi. So today I'll be talking about the solar system. So let's get started. So here we have a picture of the solar system, and I want to ask you guys, what patterns, similarities, and differences do you observe in the planets? Feel free to unmute and speak, or you can use the chat. That works too. But I want to hear your thoughts about the differences and similarities between the planets that you see here.
Maybe the first thing we can see is that Mercury, Venus, Earth, and Mars are the smaller planets, and they are rock planets. And also we have like Jupiter, Saturn, Neptune, and Uranus. First Uranus and then Neptune, and they are gas planets, and they are like the giant ones. That's like the main feature of them.
Great, thanks, Samuel. Thank you for your thoughts. Yeah, so like you said, we classify some of the planets, the first 4, the inner 4, as terrestrial planets. This means that they're composed of rock and metal, and they're much smaller than some of the other planets like Jupiter and Saturn. Jupiter and Saturn belong to a class of planets themselves called the gas giants. These gas giants are much larger than the other planets, and they're composed mainly of hydrogen and helium, 2 types of elements and gases that were really prevalent in the early solar system. Then we have Uranus and Neptune. These are called ice giants. Does anyone know why we call them ice giants? they're called ice giants because they don't necessarily have solid ice like how Earth has ice caps around Antarctica, but they are composed of ices like methane ice and carbon ice. Things that would usually on this planet be gaseous end up being solidified in their atmospheres. These are much cooler planets too, given that they're so far out. So we call them the ice giants. And these planets together make up the giant planets, which, as I think Samuel noted, because they're much larger than the other ones. And then there's a new class of planets that astronomers talk about called dwarf planets. On this image, I have Pluto and Eris, two dwarf planets way out in the solar system. And they're much, much smaller. So that's why they're classified as dwarf planets. Now, this is a distinction. You may have heard that Pluto got demoted from planet to dwarf planet. But it's just a classification that astronomers like to use to simplify models a little bit. But planetary scientists still refer to these as planets. So let's go ahead and start with a poll here. So the poll is, why are the giant planets so large compared to the size of the other planets? They had access to more matter, gas, and dust during their formation. They had access to more ices during their formation. They stole material from other planets by consuming them, or all of the above. So take some time to make our guesses or educated guesses, and we'll go over your answers.
We've got 10 out of 12 responses in so far. We'll end the poll in just a few seconds. You want to enter your answer?
Yeah, I see a few people answering in chat as well. Very good.
Seems like they've all answered too.
Okay, Dave, if we want to end the poll.
All right, let's end the poll.
So the answer to this question is D, all of the above. All of these are acceptable answers to why the gas giants are so large. And we're going to go into why here on the next slide. So thank you for your answers. So this image here shows the, again, the 8 planets in our solar system, but I put in a few other aspects of the solar system that help planetary scientists classify the planets. So these wedges are down at the bottom. If you can, I think you can see my cursor here on the screen. These wedges here indicate the types of materials that the planets had available to them during their formation. As the sun formed, its heat denied the inner planets, Mercury, Venus, Earth, and Mars, access to a lot of the solid ices in the inner solar system. These were either melted away or blown away by what we call the solar winds and the heat. So these planets only had rock and metal, which is much denser material, but it wasn't enough because the outer planets also had access to this material combined with these solid ices and gases like ice, methane, and carbon in the ice giants, and hydrogen and helium in Jupiter and Saturn. So the wedges there are to indicate the amount of material that was present. Can anyone maybe tell me what the ice line is, or where it's at in the solar system, like what occurs on the ice line?
Again, feel free to speak out your answers if you want, if you feel comfortable.
Yeah, good. I'm seeing some answers in the chat. And the asteroid belt. Right, so the asteroid belt is present between Mars and Jupiter. However, asteroids are not made of solid ices. Asteroids are composed of rock and metal. So asteroids lie just inside of the ice line there, and just outside of the asteroid belt is the ice line. That is the temperature where these solid ices start to form, which is why the asteroid belt is only composed of rock and metal. So I want to show you some of the interior slices of the rocky planets here. Firstly, I want to draw your attention to Earth. So Earth is composed of really four main parts. Does anyone know how we classify the Earth's interior? I'll maybe start us off. So the first part of Earth's interior is called the crust. This is the solid rock in which we all live on. It's very thin. It's about 30 kilometers below the, it goes about 30 kilometers below the surface. I also saw somebody point out the mantle, which is very good. Yeah. So the mantle is the part that is below the crust. It's composed of molten rock. You can think about it kind of like, not like a liquid water, but more like a Play-Doh-y plastic sort of combination or material. But the mantle is molten rock, and it moves around, which allows us to have plate tectonics. And then there's also the outer core, which is composed of liquid metal, and the inner core, which is composed of solid iron and nickel, iron being a very dense element, so it's in the center. Can somebody maybe tell me how Earth compares to the other terrestrial or rocky planets? What are some of your, based on this diagram, what do you see?
Earth is the largest terrestrial planet.
Okay, yeah. So a good thing to compare here is that Earth, a good thing to compare is Earth and Mars. We notice that Earth has a liquid metal outer core, and Mars does not. And yeah, the size of the crust varies as well. We see that Venus has a very thick crust as well as Mars, but Earth has a very thin crust comparatively. Earth is definitely the largest of the terrestrial planets. But yeah, the crust thickness varies. And then there's also Mercury. Mercury has a gigantic core compared to how big its in relative size it is. A very thin solid metal interior, and then a molten and solid crust there. But Mercury, yeah, Mars does not have any kind of liquid metal. So Mars is what we consider a dead world. It no longer has any internal activity. Here on Earth, we have earthquakes, we have volcanic eruptions. We know that the crust moves around on plate tectonics caused by the mantle motion. Mars doesn't have anything like that. Mars has no more interior activity. And so this is about as far as the terrestrial planets go for rock and metal. Keith, good question. Yeah, does Mars have Mars quakes? So here on Earth, I'll take some time to answer this question because it's very interesting in planetary science. So here on Earth, we have earthquakes because the Earth is trying to expel the heat from the inside. So the crust is cooler rock. It is, relatively speaking, the mantle, however, is very hot, and even hotter is the outer core, given that it's in a liquid state. So all of that energy from the interior of the planet is trying to escape in a way. And so that shows itself on this planet through earthquakes by mantle motion and volcanic eruptions. However, on Mars doesn't have any of that internal heat. it's all solid. There's molten rock, but this is mostly because of pressure differences. So temperature and pressure result in different phases of matter. But because Mars has no heat that's trying to escape, it contracts. And this contraction, this is also analogous that we see on the moon. The moon is also like Mars and has more internal heat. All of its heat is escaped. And so this contraction of the planet is causing deep, we wouldn't call them earthquakes. I guess you would call them Mars quakes or moon quakes, but it's due by contraction rather than thermal heat trying to leave the planet. Great question, great question. So let's move on to the interior slices of the gas giants. What's something that we see here? Can somebody point out maybe an observation or question that they have about this diagram? Maybe about looking down here at the relative size of the Earth. Yeah, great observation. So I had a great question. What is metallic hydrogen? And I saw another good comment about that the interior has some, the size, the interior of Jupiter is about the size of the Earth. If I was to take this circle here and superimpose it, Saturn and Jupiter basically have a tiny rock and metal Earth inside of them. Great observations. So the giant planets are composed of rock and metal, like we've seen. They lie beyond the ice line. And they've also had access to these hydrogen gases. So the structure of the giant planets is rock and metal on the interior, and then gaseous hydrogen and helium extending all the way out. And we see that Saturn, Uranus, and Neptune all have access to ices just beyond their rock and metal cores. So if we were able to go down into the interior of Jupiter, if we were be able to survive the pressure, we would land on a rock and metal core. Unfortunately, that is difficult. But yeah, and then I had a great question. What is metallic hydrogen? So metallic hydrogen is as you go deeper into the interior of the giant planets of Saturn, the gas giants, Saturn and Jupiter, you start to have so much immense pressure, right? You know how when you take like a snowball and you can put put a lot of pressure on it and kind of compact it. The same thing is happening in the interior of Jupiter and Saturn, but with gas. It's taking the hydrogen gas and squeezing it so much that the electrons outside of the nucleus start to behave in such a way that they can jump from atom to atom of hydrogen and start to behave like a metal. So it's a very good conductor. You may have heard that Earth has a magnetic field, and this magnetic field is because of the moving outer core, liquid outer core. In much the same way, Jupiter and Saturn's metallic hydrogen is responsible for, we believe it's responsible for its magnetic field. So that's what metallic hydrogen is. It's hydrogen compressed so much that it starts to behave like a good metallic conductor. Yeah, so we see that Saturn, Uranus, and Neptune have ices while Jupiter does not. This is because Jupiter, even though it lies outside of the ice line, it just didn't have enough material for it to have those ices. And yeah, we've seen that Jupiter does have auroras on it. Yeah, that's correct, because it has a magnetic field. So the solar wind that I talked about previously interacts with Jupiter's magnetic field, and it causes auroras just like here on Earth. So that's really good evidence that Jupiter does have a magnetic field. It's because we see auroras. Great questions, guys. Thank you so much. So let's do another poll. I want to know your thoughts here. And I might miss a few questions, TAs, in the chat. If you could also maybe help out and answer those. If not, please bring them to my attention. So Dave, if you want to pull up poll 2, thank you. So during the early formation of the solar system, which of these is correct? One of these could be correct, 2 or all 3. But I want to know your thoughts. So A, the planets exchanged mass from one another during the early solar system formation. B, the planets moved closer to and further from the sun multiple times. Or C, the planets formed at different times. So I'll give you a second to think about which one of these is true. Maybe 2 of them are true. It should be a multiple choice.
Responses are coming in.
That's great. That's great. Yeah.
Go ahead and
maybe
close the poll and take a look at our results.
Okay. So I'm so glad we all got to answer. And now let's see what the results are. So the answer to this is that all 3 of these are correct. That at one time, all of these were true for the early solar system formation, that the planets exchanged mass, that the planets moved closer and further from the sun, and that the planets formed at different times. So here I have what we call a simulation or a computer model of our early solar system. And I want to hear some of your observations that you see. Look over on the left side at what the different colors mean. And feel free to unmute yourself and tell me your thoughts, or go ahead and throw them in the chat, and we can discuss this solar system formation simulation.
It's in a spiral.
Yeah, really good observation that it spirals around, and forms and has structure. Are the circles supposed to be planets? Great observation. Yeah. So we see these red circles are concentrating, right? And forming, and they're not forming planets. They're what planetary science called planetesimals. So these are like protoplanets, planets that came before the ones that we know right now. There's areas of high mass. They move closer and farther from the sun, right? Yeah. Great observations, guys. These are all correct. So let me see if we can play this again. And so let's see if I can pause it here. So right here, we have the sun in the middle of our solar system. And surrounding it, we have an area of green, which is some mass. But beyond that is an area of really high mass, because when the sun started doing its nuclear fusion, started shining, the solar winds again pushed material away from it. It said, basically, I need some space. I'm hot. I'm going to push the material away. And it formed a nice ring of mass. And then this ring of mass sort of tapered off, right? As we saw in the second figure with the wedges, it gets less and less as you go farther from the sun. And so these are areas of density. So as we play this, we start to see some spiral shape, because the sun started spinning. And as it started spinning, it also had angular momentum, which moved all of the material around it in a similar way. And we see these lanes start to appear. And from these lanes, we start to get some, oh no, let's see if I can go back real quick. Okay, I'm sorry about that. Let's play this again. And as these lanes started to appear, they started to coalesce and condense into planets. So how many planets can you see? I'll stop it right here. How many planets are in the solar system? Can anyone just give me a number really quickly? 5. 5 again. Yeah, there's definitely some areas of high mass. But to my eye, I see 10, maybe 11 starting to form here. And there's definitely not 11 planets in the solar system, or as there is now. So a lot of these start to form together, right? And collide and merge and form bigger planets. And so this was very prevalent in the early solar system, and they get thrown out, some get thrown in, some end up really far away. And now we coalesce into what, 6 planets now, 6 really well-defined planets. So all of these things occurred in the early solar system. We'll do a third poll now.
All right, Brody, I'll get the third poll ready. And there we go. We'll launch the third poll.
So the question is, if the Earth formed inside the ice line, where did all our liquid water come from? You saw it on diagram 2, that there was only rock and metal in the inner solar system, right? When the sun ignited, started fusing hydrogen into helium, the solar winds started to evaporate all the ices in the inner solar system. And so water only occurred beyond the ice line. So where did it come from? It certainly wasn't here when Earth formed. So I want to know your thoughts.
All right, shall we wrap up the poll? I think all answers are in, and let's see the results.
So the answer to this question is C, that a majority of our water came from the outer solar system beyond the ice line and was delivered here by comets. A majority of the water couldn't have come from the rock because the rock is really hot, although there is water in the interior of the planet. At this point, there was no water. The Earth was too hot. All the water evaporated and escaped the planet. And it couldn't have come from our early atmosphere because our early atmosphere wasn't composed of hydrogen and oxygen. So water is H2O. The hydrogen was blown away beyond the ice line, and the oxygen didn't come until later when early microbes had respiration. So water, all the water that you see here on the planet, our planet is composed, has a lot of water on it, was delivered by comets or from bodies outside of the early solar system. And so how did this happen? So the Earth formed inside the ice line, which means it didn't have access to any liquid water or any water-making elements. But it got access to it because planetary scientists think that the planets, the giant planets, the gas giants, moved into the solar system, into the inner solar system, and then moved back out. So this diagram here, we see the sun on the left, and on the right is time from the beginning of the solar system formation to about 600,000 years after the birth of the solar system. And so we see Jupiter and Saturn formed somewhere beyond the ice line. There's icy asteroids beyond that and rocky asteroids inside. You can also call these comets. And then about 100,000 years before or after the birth of the solar system, the giant planets migrated inside. And at this point with them, they brought some of these icy bodies, these comets, into the inner solar system as well, and through maybe some of these rocky asteroids out. And then at about 500,000 years, they moved out into, well beyond the ice line and even populated the inner solar system a little bit more. And then at about 600,000 years, we start to have the planets developed in their current orbits. And we see that Earth down here has a nice layer of water on it. And so planetary scientists think that this water was delivered here from the outer solar system by the motion of the gas giants into and out of the interior of the solar system. And so this happened because of gravitational instabilities. The planets are pulling and tugging on one another by the force of gravity. And as they move around in their orbits, some of these tugs have effects later on. And so when you're talking about timescales of hundreds of thousands of years, you start to get some instabilities in their orbits. And simulations have been run that show that giant planets can move in and out of the solar system. So that's my talk. I want to thank you so much for all your great questions. You all were great. If you have any other questions or burning curiosities, please let me know.
It seems like we've got one in the chat from
Okay,
Bryson
so
Benjamin.
Yeah, I see that you asked about rings in the outer solar system. Yeah, this is true. So Saturn, right, has really prominent ring features that we can see. This is composed of ice, mostly, of icy material, and they're really reflectant. However, Uranus, Neptune, and Jupiter all have ring systems as well. However, they're not as well defined. So this is a study of planetary science right now about how rings form. There's a lot of good work out there that shows that rings form by the destruction of moons. So in much of the similar way, if you look at our simulation, that the planets coalesce out of a disk of material, of matter surrounding the sun. These rings form out of the destruction of moons that form from a disk of matter, similar to the solar system matter. So they get torn apart by the big gravitational forces between the planet and moons that come too close. So Saturn must have had a moon somewhere that got too close and got torn apart and gave us the beautiful ring system. But Uranus and Neptune and Jupiter must not have, or at least not as big. So I also see that the new James Webb Space Telescope images have been able to capture a picture of Jupiter's rings. Yeah, right. So you get down into you see it in a different light band, and you are able to see them through infrared. You get to know the different layers that form from the planets. Yeah, so the different layers, so there's a few ways to break it down. Great question, Samuel. And I think this will be our last one, so you guys have plenty of time for our activity. So the different layers, we see them through, so geologists study the interior of the Earth through seismic waves. So earthquakes, when they happen, they produce large seismic waves. And as these waves travel through different material, we're able to see how they change speeds, how they slow down, when they appear and disappear. And this gives us some idea about the structure of the interior of the Earth. Some waves speed up when they hit material that is denser and more compact. Some waves slow down. So it's all about seismic waves and using waves to see remotely the interior. So thank you so much, guys. I appreciate your time. I hope you enjoyed the talk and learned something, and for all your great questions. Thank you.
Thank
Dave,
you.
I'll turn it back over to you.
Great, Brody. Thank you. You can unshare your screen, and we'll go on here to the next part. So that was very, very enlightening and very engaging. Thanks for the information. I think one of the things that always astounds me is when you say that the water on Earth came from comets. Who would think that? I would not think that, but in any case. Brody, go ahead and sign off. I know you need to be somewhere. So thank you, and we'll see you again. For the rest of us remaining, we're going to begin our activity for the day, and that is going to be to create a model of the planets in the solar system. So we're going to start with, in fact, let me show you something that I did. We've done this lesson before. I just want to show you the sheet that we sent you is a place where you can make model planets and tape them or glue them in place. This is an example of something that a student did previously. And when I look at these planets, I try to think of ways that I might compare them. And we've already talked about that to some degree. We can talk about the size, their composition, what they're made of, the elements that are present. When I say size, I mean the diameter or the radius or the volume, their environmental conditions. Do they have atmospheres? Are they metallic? Do they have magnetic fields? And ultimately, we might compare them based on how far away they are from the sun or from each other. And that's kind of the idea of our lesson today. We'd like to have you create planets and appreciate the difference in their sizes, and then take that same scale and go outside and extend the solar system in a three-dimensional arrangement. So we're going to begin by saying we want to make planets scaled to the same proportion. What could we start with? What do you think we could, what do you think the starting place would be if we wanted to make planets relative to the same scale and size? What would be the starting point? What would be the best thing to relate the planets to? Do you have an idea? Anybody want to put something in chat or just speak up? What would be a good starting point to begin to make planets? Well, Keith says the sun. That's probably what I would say. If we have a sun to start with, then we can make planets scaled to that sun. So what do you think we could use for a sun? I want to make planets scaled to the sun. What could I use for my sun? Who's got an idea? I see a couple people are saying a ball. I see a balloon, soccer ball, basketball, a baseball or softball. The size of the sun will kind of determine your size of the planets and the scale in which they're distributed, how far apart they are. Now, if we started with something that was fairly small, like a softball or a baseball, think about it. Now, this isn't to scale. It's fairly close to scale. In fact, the sheet that I sent you has a little larger sun than this one. Yours is really more to scale. So when I put the Earth here, this is a reasonable scale. Based on the size of this circle, the sun, representing the sphere of the sun, that Earth is about the right scale. And so if I shrink this down to the size of, let's say, a baseball or softball, the Earth is going to be too tiny to see, practically. On the other hand, if I scale it up to maybe something bigger than a basketball, then at that scale, the planets are going to be so far away, you're going to need 5 kilometers to make your solar system. So something about the size of a piece of paper is a good scale to start with. So what I would do is take something like a soccer ball or a balloon. Okay, that is probably a pretty good size. And so there's my sun. If you have a soccer ball or another ball, beach ball, that's fine. Anything will work. You can use anything you want to. But I need to know how big this is. And based on how big this is, that'll determine how big my planets will be. So when I say how big this is, I need a convenient way to measure how big it is. So think about a circle. We could, in 2 dimensions, this looks a lot like a circle. I could determine its, what do you call the dimension that measures all the way around a circle or a sphere? What do you call that?
Circumference.
Circumference. And what do you know about circumference? How is circumference related to other dimensions in a sphere or a circle?
2 pi r.
2 pi r, okay. Or pi d. D is 2r. So whether you talk about radius or diameter, either one is fine. We're going to use a website that's going to ask us for diameter. And so I need to know the diameter of my sun. Well, you know, this doesn't have to be rocket science. You could, if you wanted to, take a ruler and just kind of eyeball where it is from one side to the other. And for our purposes, that's probably close enough. If you want to be a little more scientific, let me show you what I would do. I'm going to plug in a different camera, and I think I'm going to try a different camera. There we go. I'm going to take a string and wrap it around the balloon at its fattest part. And then I'm going to take a marker and I'm going to mark where a point where those strings overlap. Now, so I have a mark on each part of the string, and that will give me the circumference of the balloon. And then I can take a ruler, meter stick, and measure that distance. So for me, that's about 68 centimeters. Or if we're in English units, about 27.5 inches. So that's probably a pretty reasonable range for the size of the balloon or the size of the sun we want to start with. So if you're doing this at home, it's probably convenient to have another set of hands. So somebody can hold the balloon and somebody can hold the string. I've done this before. I made it look easy maybe, but sometimes it's a little difficult. So I'll give you a minute to do that if you would like to do that right now. And I'd be interested in the diameters that you come up with. Now, I will also say, if you don't have a balloon or a ball, take a piece of paper. In fact, you could take the sheet that we sent you and cut it out or make it a little smaller to fit on the page and just use a circle for your sun. That would be fine. Okay, how are you coming? Does anybody have a diameter or a circumference? So let me share my screen. I want to show you a diagram.
We've also got some in the chat already.
Okay, read what they are.
We've got 8.9 inches. We got someone with 26.5. Sebastian with 61 centimeters for circumference.
Okay, those all sound good. Okay, so here's a diagram that shows kind of what we were talking about a minute ago. We have a circle, the circumference of our balloon or our circle. And it was proven a couple thousand years ago, the relationship between the diameter of a circle, the line that goes through the center, and the circumference of a circle. And we figured out, as somebody has already said, the circumference is equal to pi times d, or pi times 2r, or d, the diameter, is equal to the circumference over pi. And so if we want to find the diameter, we can do that. Now that you know your circumference, you can divide your circumference by pi. 3.14 is accurate enough. Even 3 is close enough, but 3.14 would be fine. And you can find the diameter then of your balloon or your ball or your circle. It's that dimension that we're going to use now to scale our planets. So if you're doing this at home, do you have your diameter? If so, tell us what it is. What kind of diameters are you coming up with?
We're seeing some 6.6 inches, 20 centimeters.
Okay, 63 centimeters, 19 centimeters. So 63 centimeters. I question anything bigger than about 18 centimeters, 18 to 20 centimeters. So 20 centimeters is like this distance right here. And that seems about relative to the size of my balloon anyway. So 20 centimeters, 24 centimeters, 26 maybe would seem reasonable. 19 centimeters, sure. 63 centimeters is this big. That seems too big for me. So I think that might be the circumference, not the diameter. I want to make sure you all have diameter and not circumference. So anybody have a question? Is anybody stuck? Anybody need anything? Speak to me. If you have a question, let me hear your question. So I'm looking for diameters in the English system in the US are going to be somewhere around 9 or 10 inches. That's reasonable. If you're doing it in metric, it's about 24 centimeters, 25, 26, 19, something like that. Okay. I'm going to put a link in the chat. This is an interactive website that lets you start with the sun, and it will give you the diameters of the planets if you know the diameter of the sun. It will also give you the distance between them. So this is really cool, in my opinion. So I'm going to take an example sun. So here in the first column, I see the solar system bodies, the sun and the planets. And I see body diameter in inches, body diameter in millimeters. You could use either one. So I'm going to do this twice. I'm going to do it, first of all, in the inches system. And I'm going to enter my diameter of the sun of 9.5 inches. And if you're doing this in metric, then enter your diameter in millimeters. It would seem a little more convenient to me if this was centimeters, but if you had a diameter of 19 or 20 centimeters, well, that would be 190 or 200 millimeters. So you can enter it either way. And then we hit calculate. And when I do that, I see all of these numbers appear. These are all my diameters and distances. Never mind the distances right now. We'll talk about that in a little bit. I'm interested in diameters. So if my sun was 9.5 inches, that would be 240 millimeters. I have, excuse me, I have the diameters of the planets then in those same measurements. Now, if you did this in inches, I think we're done with inches because you don't know how to measure, nor do I, 0.033 inches. That's just crazy. So we're going to use millimeters, which makes a whole lot more sense. So Mercury has a diameter, based on my sun, has a diameter of 0.8 millimeters. People, that's less than a millimeter. That's pretty tiny. So even on my scale model here, I think this Mercury is too big because it's more than a millimeter. So what I want you to do, though, is take these numbers and copy them into this sheet here in the column where it has the diameters. So it says diameter of the sun and diameter of the planets. I'm going to pause here for a minute because I'd like everybody to have this before we go any further. Could you see the paper once more? This paper? Sure. So on my page, I have the smallest planet is Mercury. It's slightly less than a millimeter. And my largest planet is Jupiter, 24.5 millimeters. So I made these out of Play-Doh. These are close to scale to each other. Not 100% accurate, but close enough to give us an idea. So this is, you can tape, if you make planets, you can tape them down, put this on your bedroom wall or somewhere where you can look at it if you want to, and remind you of today's lesson. Okay, anybody else have a question? The sun is, you know, now I am not a planetary scientist. Mariana, I'm going to call on you. Is the sun about 10 diameters of Jupiter, or is Jupiter smaller than that?
That's a good question. I'm not 100% sure. It looks like from what you got, Dave, it is, but let me do a quick Google search.
Okay, well, let's just look at our data here. So we see the sun is about 240 and Jupiter about 24. So yeah, it seems like it is about 10 diameters.
Yeah, and I just Googled it, and yep, that's right.
Okay, so we can, that's a good question. We can get a comparison here from our data as well. Perfect. I've got a question for you, for our students. I know some of you joined the class kind of late, and you didn't have time to get materials ready, and that's okay, because you can do this anytime. How many of you have some material you want to make your planets? Show me, give me a sign, put it in chat. Can we go to that part next? We're gonna go into breakout rooms, and my TAs will guide you through doing this. We're gonna do that next. I don't want to take a lot of time, but I want to give you a chance to make some planets based on our measurements. Let's go to breakout rooms. Mariana or Amelia, are we ready for breakout rooms?
We are ready.
Okay.
How did everyone's breakout rooms go?
Okay, we've closed the breakout rooms and everybody should be back. I'd like to know, I think from the rooms I was in, everybody seemed to be doing pretty well. We did catch a few people in interpreting the scale of the ruler. You know, we're doing this in millimeters, and millimeters are the tiny lines between, so I see my finger is on 1 and my other finger is on 2. That's 1 centimeter. So the 10 tiny lines between, those are millimeters. And when you're trying to make Mercury, which is less than a millimeter, that's pretty small. It's easy to drop, to lose, which is why I think you know, if you're going to paste them on this sheet to have for later, I would just tape it or glue it. I use some glue on mine, but you could tape them in place and they're easier to keep track of. So if you didn't finish making your planets, you can do that. Now you know how to do it. and you can do it later on your own when you have time. We're going to have to finish up here in about 20 minutes. So I want to take you to the next step. And that would be, we're going to go outside and arrange the planets by distance on the same scale. So that poses a couple of questions. What will we use to mark the planets when we go outside? You don't have to take the actual planets you made, but you will at least need a marker. So some of the things we've done in the past have been, let me also tell you, I'm going to send you a PDF to print out pictures of the planets. And as an example, you're going to get photos, color photos that you can print out and have a photo for each planet. So one of the things we've done when we go outside and arrange our planets to create our solar system is use a stick. So if you have a stick, you can put the sun on a stick, the image that we send you, put the planets on a stick, and stick your sticks in the ground or the sand and make your solar system. If you live somewhere where that's not maybe convenient or you don't have sticks, you could use a rock. Just take a rock, put a rock on your photo and go to the next planet, put a rock on the photo, go to the next planet. If you have 8 friends, then get your friends, get your brothers, sisters, family members, and have them hold the planet and mark the position of the planets with people. That would be fine too. So some people use a 2-liter bottle, put a little water in it so it doesn't tip over, and tape the planet to the bottle. And then you can set the bottles according to the right distance. So I'd be interested in how your solar system, what your solar system looks like. If you don't mind, send me a photo of your solar system, and I can see how you did it. That'll give me ideas for other people maybe to suggest. So you need to know how far to go from the sun to Mercury to Venus and the other planets. And we're going to show you how to do that. On the Exploratorium website, the data that we had before, I don't have to do anything different. The data we had before has the scaled orbit radius. Now, when we say scaled orbit radius, let me show you this diagram again. Here's let's just say this is the orbit of a planet. Here's the center, that would be where the sun would be. The planet's going to go around in orbit, and it won't be perfectly circular, but it'll be fairly close. And with the sun in the middle and the planet at the circumference, the distance from the planet to the sun is the radius of the circle. So that's half the diameter, the radius. So when the table says scaled orbit radius in feet or scaled orbit radius in meters, that's what we're measuring. It's the distance between the planet and the sun. Now, if you're doing this in feet, never mind inches, just go to the closest foot. If you're doing it in meters, just go to the nearest maybe 0.1 meter. So I would round this to the nearest 0.1 meter. So that the first one would be 10, 18.7, 26, 40, just to the nearest 0.1 would be fine. However, if you want to go from the sun to 10 meters away, you need a way to measure that for Mercury. You want to go to Venus, that's 18.7 meters. How do you measure that? And so that poses a little bit of a problem. I gave you a little homework assignment. And if you had time to do it, that'd be great. If you didn't, that's no problem, because we're going to show you what to do. Who had time to measure their steps, to measure a distance, and then walk that distance 3 times to get an average? Who had a chance to do that? Samuel did. Keith did. Okay.
That Bryson did.
Okay, great. So that's the clue to measuring these distances. We can't take a measuring tape and measure them, but just take way too long. So here's the idea. You measure a distance, you walk that distance, and you have a number of steps. You did that 3 times maybe and got an average. And so that's going to give you a ratio of number of steps over distance. And we're going to use that ratio to calculate how many steps you would take to go from one planet to the next. Cameron is going to show you how to do that on the board. And so you know how to do the calculation. Cameron, are you ready?
I believe I am. I'll try to keep it nice and quick for us.
Okay.
For this example, I'll start with the sun's diameter. So I'll go to the Exploratorium website. I'll type in a body diameter of 10 inches. And like they've said, I'm going to look to that scaled orbit radius column. I'll look to Mercury for this example, and I see that Mercury is around 34 feet from us. So I'll write that up here, 34 feet. And just to make sure we understand, that scaled orbit radius, that represents the distance from our sun to Mercury here, this distance here. So I'm going to take that and I want to multiply it by that ratio he mentioned. So we're doing this across 50 feet. We have taken a number of steps across 50 feet. So the total
Cameron?
Feet, yes?
Cameron, let's get somebody who has done this and use their measurement. So
That's great.
Keith, what was your measurement for that you got when you did the steps?
I see it's 21 steps in chat. So I'll use that for this example.
Okay, so
his 50 feet, he took 21 steps. So this is our general formula here. This 34 feet, scaled orbit radius, times our ratio of 21 steps over 50 feet.
Cameron, just to be clear, where did you get that 34 feet?
That 34 feet is, again, from the scaled orbit radius column in our Exploratorium website.
Okay.
I got that by putting in 10 inches for the sun's diameter. That found everything else. And in the Mercury part, it said it was 34 feet from the sun in our scale model, of course.
Okay, great.
So with this formula, I can just grab a calculator real quick. I did the math already for this. Well, I did most of it. Now we've got the 21 feet. And this would get us in steps, because here are feet. These units, they cancel out. And that will get us around 14.28 steps. It's kind of hard to envision though, what is like 0.28 steps. So if you'd like, you can round that to, if you can see, around 14 steps. Yep.
Okay,
this is how we find our steps count.
That seems reasonable. So for someone else, Samuel had 23 steps in 15 meters. So do you want to do that example?
All right, let's see. Let me make some room. So he did 23 steps. Across 15 meters, you said?
Across 15 meters. Mm-hmm. So we'll have to change the, we'll have to get the value from the table in meters.
And if we're going to do that with the 10-inch diameter sun, or in this case, 254 millimeter sun, that meters would be around 10.57. 10.57 meters.
Okay, so Mercury to the sun, 10.57 or 10.6 meters. Okay.
If we do this, real quick calculation in your calculator, you get around 16.2 steps, which again, we can just say that that's 16 steps.
Okay, so I want to ask, I'm looking at some comments in the chat. Myra Rashid, yours was 24. Is that in, what are the units? 24 what? You can just put it in chat if you want to.
So I had 24 feet, and then the steps were 19/50, and then I'm doing the calculation right now.
Okay, then I think you know what you're doing. That sounds good.
Yeah, thank you.
I'll also just mention one little thing. So these scaled orbit radii, these are kind of accounting, or kind of assuming that our orbit is a circle, which it isn't really. Every planet's orbit is at least a little bit of an oval. So maybe this is an average distance across that entire orbit. I'm not sure what the exact calculation is, but yeah, we cannot expect these orbits to actually be a perfect circle.
Cameron, thank you very much. While students are still maybe working on that calculation, I want to go back to sharing my screen. And I want to show this table. Now, this is one of the tables, this is one of the documents that I sent you that you could print out if you want to, although you don't have to. I just want to show what these columns mean. So let me just say, scaled orbit radius to the nearest foot or 0.1 meters. This column comes from the website that we're using. So when I look at that, I'm going to get those measurements from one of these two columns, if I'm doing it in feet, or if I'm doing it in meters. So when I'm going to look at the meter column, when I see 10, 18.7, 25.9, I'd probably round that to 30, 39, I'd probably round that to 40. Those are the numbers that I'm just going to copy into this table. That's column 1 of this table. Column 2, scaled orbit radius, the number of steps. That's what we're calculating now. So you're going to take your distance here from column 1 times the ratio of the steps over distance that camera is pointing to right now. So in his first example, the 34 feet, that comes from this column, Mercury. The calculated value for the steps comes from doing that calculation. And likewise, if we did it in meters and it was 10.5 meters or 10.6 meters, that comes from the website, and the number of steps comes from doing the calculation. We're going to go to breakout for like 10 minutes and have our TAs, our teaching assistants, walk you through this calculation. Okay, let's do this in like 5 minutes because we're running out of time. From the breakout rooms that I dropped into, it seemed like we're on the right track. I'm going to talk about the very last thing now we need to think about. When you start from the sun and walk your steps to Mercury, and then you want to go to Venus, you don't want to go back to the sun again. You want to start from Mercury and go to the next planet. And so I'm going to show you, I'm going to share my screen one more time and show you the last column, column 3. So if you have, let's say, 15 steps to Mercury, and I'm just going to make up a number here, 15 steps to Mercury, 30 steps to Venus. Column 3 is the difference between those two. So if you're at Mercury, you've walked 15 steps, you go 15 steps more to Venus, and it's 30 steps to Venus, then the difference will be another 15 steps. Does that make sense? So I don't know if you can see this too well, but I made up numbers. If my steps from the sun are 15, 32, and 60, and I'm at Mercury and I want to go to Venus, I don't want to go back to the sun and walk 32 steps. I'm going to take 32 minus 15, and that'll be 17, and that's the number of steps I go from Mercury to Venus. Then if I want to go from Venus to Earth, I'm going to subtract 32 from 60, and that would be 28 steps. Okay. Does anybody have a question about that? So before we wrap up, I thought it would maybe be interesting to you to see a few photographs of people having done this. And so I'm not going to show you all these photographs. What I would like to show you is this photograph right here. So I did this with this very same lesson with a group of students over the summer. And I'm going to enlarge this a little bit. So here's a student standing at the sun, and we use these little plastic sticks to put the planets on, the pictures of the planets. So here's the sun, and I have a student here with her arms outstretched, looking back at the other planets. And I'm going to zoom in as we go. And here's a student at Mercury. Here's a student at Venus. Here's a student in the blue shirt at Earth. And from Earth, we go to Mars. Way back here is Jupiter, and the other planets follow. So the distance that we covered was about 800 meters. It's a fair distance. And of course, the distance will depend on how big your sun and planets are. So there's what the final product should look similar to. So let me just say before we go, I hope you have fun doing this. I think Brody did a great job talking about how we got here, how our planet got here. And I hope you have fun doing this lesson. If you have any questions, email me and we will respond. We'll stop there. If you have any comments, please send them to me, send me your photographs, and we'll see you next time in SMAP, which will be the topic of black holes. So black holes is something that some of you have asked about, and we're going to do that in our next session. That'll be October 22. Okay?
Thank you. Bye.
You are welcome. Bye-bye.
Yeah.
Thank you very much. See you all.
Bye-bye.